Okay, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Sang-Il at IBS and KAIST, who's going to be talking about obstructions for matroids of path width at most k and graphs of linear rank width at most k. Go ahead, Sang-Il.
Okay, thank you. Thank you for inviting me. It's my pleasure to give talk here at the Graphs and Matroids seminar. So this talk is indeed about graphs and matroid. So this is about the obstructions for the class of matroid of path with most k and the class of graphs of linear rank with most k. And this is joint work with Mamado and Eunjung and Ojang. So I can start with the theorem. So here are two statements of the paper. So the first theorem says that every pivot minor minimal graph having linear rank is bigger than k. So, or another way, pivot minor obstructions for class of graphs of linear rank with most k has at most 2 to the k square many vertices. So we give explicit bound on number of vertices for each of these obstructions. And the second statement is that for any fixed finite field f, among all minor obstructions for the matroid of path width and most k, f representable ones have size bounded by this function. So 2 to the size of f to the k squared elements. Right? So we, in both cases, we give explicit function for the size of these. Okay, so that's the main theorem. So the proofs of both statements are quite similar. And even though we have many matroid experts here, I will probably mostly state it in terms of graphs, but later you will see why the same technique will go through. Actually, it's simpler to prove for matroid. Okay. So let me quickly go through the motivations, right? So whenever we have a minor closed class of graphs, there's a finite set of obstructions, right? That says that there's a finite list of graphs so that this class, some graph belongs to this class if and only if that graph doesn't contain any of the graph in the list as a minor. And the proof is non-constructive. So this proof doesn't give you any upper bound on the size of the forbidden minor. And we have many width parameters known, like path width, tree width, branch width for graphs. And all of them, when you take a minor, the numbers only decreases, not increases. Therefore, the class of graphs having path width at most k, or tree width at most k, branch width at most k, all of these classes are minor closed. So which means that by this this theorem, there exists a finite list of forbidden minors. But this theorem doesn't tell you the explicit upper bound. And there are results, like in 1998, Lagergren proved that every minor obstruction for the class of path width at most k has at most that many edges. So this is about path width. For tree width, the minor obstructions have at most 2 to the 2 to the k to the 5 edges. And Jim, Bert, and Neil, and Jeff proved that every minor obstructions for matroid of branch width and most k has this many edges. And in fact, you can, I mean, they proved it for matroid, but as a corollary, it implies that graphs of branch width and most k has this many edges. So for many of these parameters, you have explicit number, but not for the it was not known for pathways of Matroid and also not known for linear rank width of graphs. So I will describe what the linear rank width of graph is. So before going right into the definition, I will describe the connectivity functions. So whenever we have a partition of the ground set or edge set, so in this case, it's the edge set. If you have a partition of the edge set, then normally we measure the standard connectivity in a graph by counting vertices meeting both parts. So let's write it as a v of x. This is a standard connectivity function in graphs. In a matroid, we could measure the connectivity by this function, right? Rank of x plus rank of complement minus rank of everything. This is the standard connectivity function for matroid. And for these functions, you have common features. So the common feature is that they satisfy the submodular inequality, and it's symmetric, so it doesn't matter whether or not you take a complement. And we just add them, we normalize them, so empty set gives you 0. Then we call it a connectivity function for finite set V. And then there's a different way of defining connectivity function on graphs. So instead of considering the partition of edge set, now we consider the partition of the vertex set. And then when you have a partition, then you look at the matrix, 0, 1 matrix, whose rows are from one side and columns are from the complement. And entry is 1 if the corresponding row and column vertices are adjacent and 0 otherwise. And I consider it as over the binary field. So this is the this is so-called the cut rank function. And it turns out that it satisfies all the axioms, like it's symmetric, it's submodular, and empty set gives you 0. So you can think of this as one of the connected functions for graphs. And it works well with dense graphs because when you, this cut rank function, the value will be small if almost all is 1, right? So when you have a small rank matrix, and if you change zeros to 1, 1s to 0, you still have a small rank, just differ by 1. So that coincides with our intuition that if the cut is simple, then when you complement all the cut from left to right, you still have a cut which is simple to describe. So here's an example. So in this graph, you look at the set of red vertices, and the cut rank of that set is 2, because we have this 4×3 matrix. And now there's a point. So since the underlying field is binary field, so second row plus third row is the fourth row. So rank of this matrix is 2. So the cut rank of that red set is 2. And whenever we have a branch connectivity function, we can define branch decompositions. This was due to Robertson and Simmer. And so let's say if this connectivity function is defined on the subsets of finite set V, then we consider the pair of subcubic tree. So this is tree whose internal node have degree 3 with a bijection L from this finite set V to the leaves of the tree. So I label these leaves by numbers representing each elements of V. So such a pair is called the branch decomposition. And then for every edge, I have a canonical partition of the ground set of, the V, right? When you delete it, you have two components. So one side is, let's say, 1, 2, 3, 4. The other side is its complement. The width of an edge is the f of this value, where AE denotes one part. It doesn't matter which side you take because this function f is symmetric. So that's width of this edge. And then width of the branch decomposition is the maximum width of all of those edges. That's that's width of the particular decomposition. And then branch width is minimum possible with overall possible branch decompositions. So that's a branch width. And if you use the standard connectivity function for graphs, so counting vertices for the partition of edges set, then you get the definition of branch width of a graph. And if you use the matroid connectivity function, then you get a definition of branch width of matroid. Sometimes people add 1, so but anyway, depending on the reference, I might have to add 1. And if you use the cut rank function, then this is the definition of a rank width of graph. Now, how do we define linear rank width? Well, we will restrict the trees. So in the definition of branch decomposition, I will restrict the trees to caterpillars. Caterpillars are trees where they have a particular path called the spine, where every leaf is adjacent to one of the vertices of the spine. So that's a caterpillar. So I will, if we restrict these caterpillars, then the branch width is path width of the connectivity function. But here's an alternative definition. So instead of, because normally for these edges, we don't really care about the width because the width of single elements is usually small. It's almost 1 for matroid. So alternatively, we could say that, well, let's just consider linear layout as a linear ordering of the elements in the ground set. So in this case, this is E1, E2, right? So E1, E2, E3, En. Then that defines a linear ordering, right? And then since these edges already have small value, it's okay to just worry about those edges, right? And the width of that decomposition, that tree, caterpillar, is same as that, right? So I look at particular cut, and then this set is E1 up to EI, right? So we compute the f of E1 up to EI and take a maximum. Let's define that as a width of a linear layout. And the path width is the minimum width over all possible linear layouts. And then obviously branch width is less than or equal to path width because branch width considers more trees, so there's more chance to have smaller values. And then if we use the standard connectivity function for graphs, then we get the definition of linear width, studied by Tillikos and Baudelander, I think. And then if you use the standard matroid connectivity function, then you get the definition of path width of matroid. And if you use the cut rank function, then you have definition of linear rank width. All right. Now, so this is the definition of a linear rank width of a graph. And then I should say what pivot minor is. So there are operations that preserve the cut rank function. So these operations, one of the operations is called the local complementation, and the other is called the pivoting. Oh, there's a typo. Anyway, so local complementation is to replace a subgraph in the induced by the neighborhood of vertex V by its complement. And so if you have a graph like this, then this becomes local complementation. We usually identify G star V. And pivoting can be actually defined by a sequence of 3 local complementations. So for an edge E, so let's say E is UV, the pivoting by UV is defined as G star U star V star U. But in fact, there's a graphical description. So here's a U, here's a V, and then you look at the common neighbors of V, neighbors of U. And what you do is to flip edges between these 3 sets. And then change the names of U and V. So this left vertex become V, right vertex become U, and edges between them are flipped. So that's the description of pivoting. And one of the key observations is that these operations never change the cut rank function. Well, it's not difficult to see, like if you have a set X, let's say I'm considering X, and let's say I have a row for V here, and then these are the people in X, these are people in X. Then neighbors of V will have 1 here and something. So when you take a local complementation, then this is the this is the part where you change the zeros to 1, 1 to 0, because here's a vertex V, neighbors and non-neighbors. Let's say this is X, right? So where do we change? This is the only changes along this cut. So if there was 1, then it becomes 0, and 0 become 1. And you can simulate that by adding this row to all the rows in X. And that doesn't change the rank because 1 plus 1 is 0. So that's why these operations make sense when you study the property with the cut rank functions. And we say that a small graph H is a pivot minor of big graph G if I can obtain H from G by sequence of vertex deletions and pivoting. And similarly, we say vertex minor if small graph can be obtained from big graph by a sequence of vertex deletion and local complementations. So every pivot minor is a vertex minor because pivot operation can be written as a sequence of local complementations, but not every vertex minor is a pivot minor. So here's some example, canonical example class of graphs having nice description in terms of pivot minors and vertex minors. So that's a circle graphs. Circle graphs are intersection graphs of chord in a circle. So you have circle and several chords. Then I can draw 1 vertex for each chord. Okay, so maybe I should better put numbers. So 1, 2, 3, 4, 5. And 3 is adjacent to 4, right? Because they intersect. 3 and 5 intersect, and 1 and 3 intersect, and 1 and 2 intersect. So this graph is called the circle graph because it's intersection graph of this chords in the circle. And Boucher proved that graph is a circle graph if it has vertex minor in this list, these 3 graphs. And Jim and I proved that the graph is circle graph if and only if it has no pivot minor in these 15 graphs. Okay, so we have something like Grotowski theorem for pivot minors and vertex minors. And in fact, you can actually prove theorem on planar graphs from here. And the key thing is that these are related to the fundamental graph of binary matroid. So for people minors, bipartite graph stays as a bipartite when you take a P1 minor. And so we are like, if you want to imply this theorem, you only need to look at the bipartite graphs in the 15 of these graphs, and then only 3 of them are bipartite. One is the cycle matroid of K5, so the other is K33, and there's a Fano matroid. So that's how you can deduce Krotowski theorem. Anyway, graph minor theorem, the minor closed class have finitely many minor obstructions. That's Robertson-Simmers graph minors theorem. And we have a similar conjecture, analogous conjecture for people minors and vertex minors. As we have seen in the circle graph case, you only have a finitely many obstructions. And I had a theorem saying that each people minor closed class of graphs has finitely many obstruction of bounded rank width. So another way of saying this statement is that graphs of bounded rank width are well quasi-ordered by people minor relations. But this already implies that for the class of linear rank width and most k, there are only finitely many people minor obstructions. Why? Because each of those obstructions have a linear rank width exactly k plus 1. So therefore, rank width at most k plus 1. So we can apply this. Then there are only finitely many people minor obstructions. And by the same logic, the class of graphs of rank width at most k has finitely many people minor obstructions because each of the obstructions have rank width k plus 1. So therefore, there are only finitely many obstructions, people minor obstruction for all these two classes. So I will later show you more explicit bound for this. So here are known things about people minor obstructions for rank width. So a graph has rank width at most 1, if and only if you don't have a people minor in this set, particular 2 graphs, right? C5, cycle ranks 5, and cycle ranks 6. And for people minors, for rank width k, we had a explicit bound. So 6 to the k plus 1 minus 1 over 5. And the proof is almost same as the proof for Matroid case, proved by Jim, Bert, and Neil, and Jeff. So for rank width, we have explicit bound. I tried to improve the numbers a little bit. So I gave a talk about this a long time ago, but the paper, I didn't complete the paper until recently. So this proves that for the case when k is 2, you could improve the numbers a little bit. So instead of 40 something, you get 16. And also you can improve this number by a little bit. Now I can multiply something because this proof was based on induction. So when you improve any number for smaller case, you improve numbers for later case. Anyway, for all these things, we can deduce the following corollaries that, so in 2007, Bruno Cruzel and I had a theorem saying that for any fixed graph H, we can construct some logic formula describing that this fixed graph H is a people minor of input graph. So by combining this with that, I could write a logic formula to describe whether or not the rank width is at most k. So for each fixed k, there's a logic formula, right? counting monadic second order logic formula. So once we have a logic formula, then there's also algorithm. For any monadic second order logic formula, in cubic time, we can decide whether or not input graph satisfies this logic formula. Okay, or that graph has rank with symbols k. Can you hear me? Yeah.
Yeah,
So
I think it just
connection was-
cut out for a second, but it seems to be okay right now. Yeah.
Right. It says it's unstable connection a little bit. All right. So that was the status for graphs. What about the linear rank quiz? So Adler and others proved that the obstruction for linear rank quiz 1 are exactly those 8 graphs as a pivot minor. So for linear rank quiz 1, we have explicit list. And for linear rank quiz K, Mamadou and Ojang had a paper proving that among the obstructions, the rank quiz 1 obstructions have at most that many vertices. So there could be other obstruction, but they were only able to prove for rank quiz 1 obstructions. So our theorem says that pivot minor obstructions for linear rank quiz K has this many vertices. So as a corollary, we can actually construct a logic formula, right? That decides whether or not linear rank quiz is at most K. And as far as I know, this is something new, okay? So until this theorem is proven, we didn't know how to construct it. I mean, we knew such a formula exists because of well-quadratic ordering. We knew that there exists some formula, but we didn't know how to construct it. Now, if I want to construct it, I can just search all graphs up to this many vertices, decide whether or not it's linear rank quiz is at most K, and then write down the formula. And as a corollary, we can decide whether or not linear rank quiz is at most K. But this corollary was known already. Now, let's look at the Matroid version. So we have an analogous Matroid version. Instead of linear rank width, we have path width. And instead of these two, we have the size of field. And they were kind of, they were results that is not really a lower bound, but it's something. So it says that there are many obstructions. So Jisoo and Ojang and I had a paper saying that there are at least this many graphs in the list of pivot minor obstructions. And we even proved that they are pairwise, not locally equivalent. So you cannot obtain one from the other by a sequence of local complementations. And for Matroid pathways, Dimitrios and others proved that the minor obstructions for Matroid pathways at most K should contain at least K factorial squared distinct Matroid. So there are many obstructions, but this doesn't say there's a big obstruction. I mean, it could say if you take a log of something, but that will become silly bound. Okay, so here's the algorithm, right? I already mentioned that we knew it from other results, not just from here. So the thing was that recently in 2017, Jisoo and Eunjang and myself had a paper proving a cubic time algorithm to decide whether or not linear rank width of graph is at most K. And if the answer is yes, then it also output the optimal layout. Okay. And in the same paper, we also proved that for matrix pathways, we also have algorithm to decide whether or not pathways of matroid is at most k, and find the optimal linear layout if the matroid was represented over some fixed finite field. And not only this result is related to us, but actually we use their tools. So the algorithm is based on dynamic programming. So at any moment, it will store all possible partial solutions in a compact way. And then later on, whatever things attach it, we would be able to decide whether or not this substructure can be extended to the global optimal solution, whether or not it has path with most k or linear rank with most k. So we have this constant size data structure, and that was essential for the algorithm. And we are going to use this tool for our proof for obstructions. So here are the three main tools, ingredients. So the first one is the existence of linked linear layout. And this is due to Nakamochi. And the second one is touch linking theorem. So for matroid, we just use touch linking theorem. For graphs, pivot minus graphs, I had an analog for pivot minors. And then the key ingredient is this data structure called the B trajectories used in their algorithm by Jisoo and Eunjung and myself. So let me go through each of them. So given a linear layout, right? So you have a E1 up to En. We say this is linked if, okay, so here is like, say E1, E2, E3, En. So whenever I choose I and J, so whenever I choose, here's the E1 up to EI, and here's the EJ plus 1 up to En. So I choose these two cuts. This just says that minimum order separation, separating this set from the right-hand side, minimum order separation, the order of the minimum separation is realized by one of these cuts in the decomposition. So this is what's called linked. So for tree-tracing pathways, there's a similar theorem that whenever you have a tree decomposition of width k, then there's a linked tree decomposition with k, which means that if you have a two backs of size, same size, and if all the intermediate backs have size bigger than that, then you have a k path connecting the first back to the last back. And the same thing is true for any connectivity function. So this is true for pathways for any connective function. So Nakamochi's proved that if there's a linear layout of width and most k, then there's a linked linear layout of width and most k. And this is conference paper, and he never even bothered to write this theorem in this form. He had an algorithm to find the linear layout of a connectivity function, but his output is always linked. Because if you look at his algorithm, then output is always linked. So therefore, I can state it this way. I mean, there might be an earlier reference, but anyway, this is the earliest that I found. And here's a linking theorem for pivot minors. So maybe I should state for linking, first state the linking theorem for matroid. So imagine that I have a big matroid M, and there are two sets X and Y. Now, in the Mangers theorem, we say that either you have a many paths or there's a small cut separating X to Y. Now, I can describe cuts in a matroid, but I cannot describe many paths in a matroid easily. So instead of that, what Tut did is, whenever you have a separate disjoint sets x and y, you can find the minor on x union y, where this cut realized the minimum order separation from x to y. Okay, so there exists a minor n on x union y such that lambda n of x is equal to minimum order separation e minus y. Right, so that's the Tut's linking theorem, and we had also a version for pure minors. It's the same thing, except my y is the complement of y here. Okay, so everything is same. So whenever we have a graph, and here's x and something, then I can find the pivot minor where cut rank of this is equal to the minimum order separation between x and this thing. Okay, so that's the analog of Tut's linking theorem for pivot minors. Now, why is this useful for the graph case? Well, let's say if this is happening, then I can apply pivoting and delete vertex deletion so that if I delete vertices in the middle, the cut rank is preserved. So I can apply pivoting first. So that will be used later. But this step is not used in the matroid. Anyway, so let me describe the sketch of the proof. Right, so let's imagine that we have a pure minor obstruction for graphs of linear rank with most k. Then obviously it has linear rank with exactly k plus 1. So there's a linear layout of with k plus 1. Then by Nagamochi's theorem, there's a linked linear layout of with and most k plus 1. So I draw this green bars represent the width of this each cut, right? So the first cut is width is small, and second cut width is slightly bigger. 1, 2, yeah, maybe this is 0, 1, 2, 3, etc. So each of the bars represent the width of the cut. And then what we're gonna do is find many cuts of the same width so that they are pairwise linked, meaning that all the other cuts in the middle have higher value, higher width. This is possible because the graph is big, so the number of cuts is huge, but the height is bounded, right? You have only k plus 2 distinct values, 0 to k plus 1. So there are only k plus 2 distinct values, right? So by pigeonhole, you can find some cut with many values repeating. In addition, all the values in between are higher. And then we use Tut's linking theorem between the first of these cut and the last of these cut. Okay, so between these two cuts, apply Tut's linking theorem. Then we can apply pivot operation to make sure that deleting all of them still doesn't decrease the cut rank. Okay, and applying pivoting doesn't change anything because cut rank is same. Now we think of the algorithm for dynamic programming, and the dynamic programming algorithm of Jisoo and Ojung and myself, Jisoo and Eunjung and myself had this something called the full set, meaning that so it scans this linear layout from the left to right. So at any moment, I compute the full set and then I added one more cut. I update the full set, so it keeps going. And the amount of possible number of possible distinct full set is constant, but there are too many cuts. So by the Pisonal principle, there will be 2 red cuts such that the algorithm will have exactly same status, exactly same full set here and there. But of course, when you say exactly same, I mean, it's up to certain linear transformation we will need later. Because these full sets are a collection of something which is described by subspaces of some vector space. And these two are actually not on the same vector space. So I have to find a linear transformation to match them up. But anyway, we will find a pair of things having same status in the algorithm. Which means if I attach the right-hand side over here and right-hand side over here, the algorithm will output the same answer. So the algorithm to decide whether or not linear rank width is at most k will give you the same answer. And this was linear rank width k plus 1. So the algorithm will say no for this input. So linear rank width is bigger than k. So which means that the same algorithm will answer the same thing for this input, right? This together with that side will still have a linear rank bigger than k. But this was obstruction. So if I delete something in the middle, it should have a linear rank with at most k. That's contradiction. So that means the size of this is bounded by some function. So that's how we finish the proof. So now you may wonder, like, what are these vector space? How do we get a vector space over the thing? And for matroid, this is very natural, right? When you have a matroid, you already have a vector space. So nothing to worry. And here's a canonical transformation from graphs to something called subspace arrangement. This is just collection of subspaces. So subspace arrangement is just collection of subspaces. And the linear layout, I mean, I can define linear layout of this collection as a permutation of these subspaces. And we can also define path width of this collection, like width of linear layout is, so you use this as your connectivity function. So we have a subspaces V1, V2, V3, Vn. Now I look at any cut, then what is the width connectivity function? Well, it's the dimension of sum of the left-hand side intersection with the sum of the right-hand side. And then I take a maximum. So that's the width of linear layout. And the path width of subspace arrangement is the minimum width of all possible linear layouts. And the subspace arrangement contains matroid, right? So in the sense that if you put each VI as one-dimensional or at most one-dimensional vector, vector space, subspace, right? So if you have a matroid, then represented over some finite field, then, I mean, you don't have to have finite field, but if you have a representable matroid, then take each VI as the span of each element in the matroid. Then this whole thing is same as the path width of matroid. But now I want to describe how you get the subspace arrangement from graphs. So I mean, here I've written some more in a complicated notation, but maybe it's better to look at this picture. So I look at the identity matrix together with the adjacency matrix. So it's an n by 2n matrix, right? Now I will collect the first column with of identity matrix and first column of the adjacency matrix. That's what I mean by EI and VI. So this is E1 and V1. And take the span of E1 and V1. That's going to be my first V1. Okay, and span of E2 and V2, that's V2. And span of third column of identity matrix and third column of adjacency matrix, that's going to be V3. So we collect the two-dimensional subspaces, and then it's a subspace arrangement arising from graphs. So why do we care? Well, the thing is that the connectivity function arising from this subspace arrangement is exactly twice the cut rank function. So it's fairly straightforward to see. Right, so you have an identity and adjacency matrix here. Now let's say this is X. And am I doing correctly? Yes. Right, so what is the span of left-hand side intersection with the span of right-hand side? Well, since X contains identity part here, so I can assume that this is 0, span doesn't change. Right, span of this plus that doesn't change, even if I change this to 0. What about the complement? I have a span of the complement. Well, because we have identity parts here, even if I change this to 0, the span doesn't change. Now I look at the intersection of X and intersection of span of X and span of complement, and then the intersection can only occur along the dimension of the rank of this matrix. Right, so rank of this matrix plus rank of that matrix. But these are symmetric, so rank of that is a cut rank. So this plus that is twice the rank, cut rank. So that's how we have these relations. So this canonical, if I have this canonical subspace arrangement from graphs, then path width is exactly twice the linear rank width. That's how we get vector spaces. Then how do we encode all the possible information into finite structure? That's where we use the idea of, we use bit trajectories. The idea is actually from the Baudelaire and Clark's paper for true width and path width of graphs. So basically the key thing is, okay, maybe I will go through here. The key thing is if I have a E1 up to En, for any cut, I'm gonna encode the, okay, not E1 up to En, it's the subspace arrangement. V1, V2, Vi, and Vi plus 1 up to Vn. Now, for the left-hand side, I take the sum of them, but intersection with particular fixed subspace B. So that's what I remember. So Li is the sum of the left-hand side intersection with the B. So here's a sum B. So I have like left-hand side, and then I have right-hand side. So Ri measures the sum of the right-hand side intersection with B, and maybe the left-hand side and right-hand side may intersect, right? They may span some vector not witnessed by B. So the amount of that is measured by this number. So lambda I is integer that shows you the dimension of the intersection in addition to what's shown inside B. And the triple of Li, Ri, lambda I is called the what's in that paper we call it statistics. And the sequence of statistics is what's called the bit trajectory. And so this is the canonical way to construct this bit trajectory, but then there's operations to compress this information. So more formally, we define bit trajectory as any sequence of statistics where left-hand side is increasing sequence of subspaces, right-hand side is the decreasing sequence of subspaces, and then we have the first and last condition, and the width of the trajectory is the maximum lambda value, where this lambda is not about the matrix connected function. This is about this number. And so far, there may be a lot of bit trajectories, but it turns out that you only have to remember finite amount. And here's an operation. I mean, you don't have to know exactly, but the one key operation is that when you have two lambda and these things Li, Lj, let's say Li is equal to Lj and Ri is equal to Rj, and lambda is changing, like let's say 3, 4, 5, 7, 6, and something like that, 8, let's say. So that 3 is minimum, 8 is maximum. These are all sandwiched between 3 and 8. Then the intuition is that in the algorithm, you don't care about these numbers. As long as 3 is safe, they will be safe. When you glue things together, the widths go up, right? As long as 3 and 8 are safe, then they will all behave in the same directions. So all of these numbers will be added by 1 or 2, or deduced, subtracted. So they will all move together, and we only care whether or not the width will be bigger than k or not. So as long as 3 and 8 are safe, then anything in between will be safe. So we can delete them. So this is what's called the this is what is described here. So I can delete all the subsequences if it's sandwiched by minimum and maximum. And that's in the paper by Baudrand and Clarks in 90s. That number of such sequences obtained by deleting all these things is bounded by a function of k. And by using that, we were able to, so a bit trajectory is compact if you cannot apply these operations any further. And then by using the Baudrand and Clark's theorem, we were able to show that number of compact bit trajectories is bounded by this explicit function. Okay, so you don't have any dependency on size of input. It's just constant, right? But for given zeta, so that zeta is the dimension of b, but eventually we will put this to be k plus 1 or 2k plus 1. 2k plus 1 for graphs, because everything is doubled. For matroid, we put k plus 1. So this is going to be the key part. And then the full set is set of all compact bit trajectories, which is bigger than, which dominate another bit trajectories that can be witnessed by past decomposition of width and most k. So that's what we realizable. So we collect all compact bit trajectories gamma, which dominate a realizable bit trajectory. So that's the collection of full set. And this paper doesn't have any complicated things because all the difficult theorems are proven in the algorithms paper. So as a corollary of the algorithm, we knew that if two configurations have same full set, then the answer will be same. Yeah, so if two things have the same full set and left and right, then the answer can be obtained. So basically, this is the intuition. Okay. maybe I talk too much detail, but I hope you get the idea. All right, so this is the final slide. So the first question is, can we find an upper bound for the size of minor obstructions for matrix pathways, independent of the size of field? So far, the size of field is crucial for our application because in this definition of B trajectory, we really count number of subspaces of certain dimension, and number of subspaces depends on the size of field. So if field is too big, we have no idea how to control them. And the second one is, can it have a real lower bound, right? Can we find the lower bound where this function is actually needed? That might be doable. Okay, so these are open problems. So thank you for your attention.
Thank you so much, Sang-il. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3.
Thank you.
And does anyone have any questions?
Well, I asked you this question before, but it's basically, it would be nice to have it in general for matroids.
Right.
And actually, slightly more general, I wonder if there is a well quasi-ordering type theorem for matroids where if you just care about connectivity. And the answer is no if you don't ask the right question. Like there's lots of questions you could ask, and the answer to all the questions is no. But this one I don't know the answer to. So suppose I give you a fixed integer k, and now I want to find. So I'll say that one matroid embeds in another if I can embed its elements in that matroid, so that whenever you have two sets in the first matroid that have connectivity less than k, less than or equal to k, then in the bigger matroid, the connectivity is at least what it is in the smaller matroid. And so for every given k, you have an order operation on a containment relation on matroids. And I wonder if that's well quasi order.
I see. So it's more relaxed than matrix minor operation. So
right, but it would basically tell you that for any width parameter you could ever cook up, there's always going to be a finite list of excluded obstructions. And if you have a finite list of excluded obstructions under this containment relation, then you also have a finite list of minors, because there's this theorem which allows you to do connectivity intertwining, so that if I have a collection of sets that I want to keep the connectivity of, I can remove all but a bounded number of other elements keeping that. So this would say that for any width parameter you could ever imagine in a matroid.
I see. So even though matroids are not well controlled, for width parameter you could potentially get the finiteness of obstruction. That's what you mean, right?
Yeah. So if what you're after is only to do with connectivities, then you always get a finite list. That's really the question.
Wasn't there a paper by Peter Hilani saying that there are like anti-chain matroid of branch with 3 or 2 infinite anti-chain but maybe your
There are infinite anti-chains of matroids
Yeah.
of width, but they're decided on things like the fact that they're anti-chains. So you can get spikes, and
right.
but it's not the low order separations that are different. They don't differ on low order separations. They differ on high sets that have high connectivity. So they're basically differing on hyperplanes. You're basically relaxing circuit hyperplanes to get these differences, and those circuit hyperplanes have very, very high connectivity. I mean, their complement may not be spanning, but it's almost spanning. So these things have connectivity. So the connectivity value of those sets would be very close to the rank. But if you
interesting, yeah.
If you fix the K, then probably, I mean, it would be trivial that for spikes, you have well quasi ordering. Like for my notion, spikes are trivially well quasi ordered.
Yeah, interesting question.
And then the next thing is to get explicit bounds for the linear case, which is another issue. But for connectivity functions, I think that there should be. Right? There's also a minor operation on connectivity functions. And if I tell you that I've got a connectivity function, and I tell you that every singleton has connectivity 1, there should be some obstructions for a bound on the size of obstructions for that too. And in fact, my containment relation is a connectivity function thing. So there's nothing really matroidal about it. It's really a connectivity function containment operation. And I wonder whether that might be a well quasi order on connectivity functions.
I see. So
unitary connectivity functions. Connectivity functions where all the singletons have connectivity at most 1.
If it allows connectivity at most 2, then it would be more useful, because then it will imply, actually it's okay. It's okay even with the 1. Yeah, that will imply linear ranks as well.
Yeah, most 2 is fine as well. It just has to be bounded.
All right. Does anyone else want to jump in with a question or a comment? All right, maybe I'll end the recording there. Thanks again, Sang-Il.
Thank you.